Okay, so hopefully you're not just jumping right into the second video, right? Hopefully you tried the problems and now you're here to see if you did them right or not. And so this is a little bit more complicated of a function. It definitely is closed, but is it continuous? And the square root, we should be cautious that we can't take square root of negative numbers over the reals. Well, that would happen if you chose values that are bigger than 3. But notice our domain, we're between -1 and 3. So we are continuous. It's not as easy to see right away. You have to think about that for a second. But yes, it's continuous. And we are on a closed interval. So all of our extrema will be the critical values. Derivative is 0. Derivative is undefined. And you should already know that your endpoints are always where it's undefined. But you might pick up other things. And so I would do the product rule here. 4x and then the square root of 3 minus x. So let's see, derivative f prime, derivative of 4x is 4. Leave your square root function alone, 3 minus x, and then plus, leave 4x alone, and the derivative of that is 1 over 2 of those as roots, and then, sneaky chain rule, -1. And so this is the expression we're going to eventually want to set equal to 0. So 3 minus x, 2 and 4 cancel, and there's a negative, and the x will go on top. So minus x over the square root of 3 minus x. Simplify. Oh, and my 2. Now, so I'm seeing this, and I all of a sudden have something in my denominator. And so there's an issue here when x is 3. 3 is critical because that would make a 0 in the denominator. But I already knew that 3 was critical because it was an endpoint anyway. But it's just good to always check. Sometimes your derivative might give you, a function like this did, where you have to be suspicious about what's happening in that denominator. Okay. So now that we know that 3 is critical because it's undefined there, also because it's an endpoint, let's check out when this is 0. And so a couple different strategies. Maybe the best strategy, or the thing that's coming to my mind right away, is just to multiply this whole thing by the square root of 3 minus x, because 0 times that is still going to be 0. And then when I do this times 4 of the roots, it just goes away to become a normal 3 minus x. And then when I multiply this to here, it actually cancels the denominator to get a 2x. I mean, that, right? I mean, look how nice I cleaned that up. That, to that, to that. Okay, so now I have this equation here, much simpler to solve compared to the square roots. So here we go. 4 times 3 is 12, minus 4x, minus 2x. So let's see, that's -6x, so 0 equals 12 minus 6x. So it looks like x is equal to 2. So we have 2, we also have -1, and we have 3 as our 3 critical values. -1, 2, and 3. Okay, so putting -1 into the function, 3 minus -1 is 4, square root is 2, and that's 4 times -1, so it's -4 times 2, or -8. You put 2 into the function, and you get 8 times square root of 1, which is 8. You put 3 into the function, and I believe you get 0, because 3 minus 3 is 0. Okay, so then, again, here are 3 values. The absolute max appears to be when x is 2. The maximum value is 8. And then it looks like the absolute minimum on this closed interval is when x is equal to -1, and that value is -8. Okay, example 4. Now here's where I wish I could be here in class, because this is like a classic Mr. Brown is setting you up to be tricked, right? He's setting you up to make sure you're paying attention, because if you read this very closely, especially the underlined word, you would have seen that I've already given you the derivative, right? I've already given you the derivative, okay? And so if I already know what the derivative is, and I've given you that derivative on this closed interval, I guess I should have also said that f was originally continuous. We'll make that assumption since the derivative is continuous. It's just a polynomial. what are the critical numbers? So, critical numbers, anytime the derivative is 0 or undefined. Well, this derivative is never undefined, but in terms of when is it 0, it's 0 at 1/2 and at -4, at 1/2, at -4, but then we also realize that the endpoints are also critical, -2 and 5. Now we don't know what this function is, so we can't really put their values here, but in terms of like what their y values are, but critical numbers are just referring to the x components, okay? So, but here's where I'm tricking you, because this interval, -2 to 5, -2, 5, but guess what? Outside the interval. So there's really only 3 critical values in that interval. Yes, this is critical. Yes, this is suspicious. Yes, that's when the derivative is 0. But it didn't fall in my interval, so I throw that -4 out. So that's why I wish I could be here, like, aha, got you, right? So, sorry, Andrew Lee, got you. So now we can see who is watching the video, because I called out Andrew Lee and getting it right, or I guess getting that wrong. Okay, awkward moment over. Yeah, see, it's just like I'm in class, all my awkward moments. Okay, so number 5, another derivative. Again, emphasis derivative, emphasis derivative. Here is the derivative. So right away, -5 and 1 are critical. I can make my list here of my x values. We don't really know what the function values are because we don't know the function, but that's okay. We're just listing out x's. When is this thing equal to 0? Well, 1 and -1, right? If I set this equal to 0, that would make the numerator equal to 0. I already have a 1. I don't have to list it twice. It's not like double critical, just once. But -1 works. And then also don't forget -4 is in the denominator. That would make that derivative undefined. Okay, are all of those values in this interval? 1, -1, -4, and -5? Yep, so there they are. Okay, now, number 6 is more of like a visualization of like, well, what happens if, all right? What happens if you don't have a continuous function, or you don't have a closed interval, or both, okay? Basically what that means is you're not gonna have a guaranteed absolute max or absolute min. And so like, for example, A, here's a function, now it's continuous, but it's an open interval. Now this function definitely has an absolute minimum. The absolute minimum is right there. But this is one of those weird things where there's not a absolute max. This you can never touch. So it's like there's a boundary, right? There's definitely an upper limit. Nothing's higher than that value. But you can't touch it. You can't get there. No matter how close you think you can get to the upper limit, the upper y value, you're never at that point. So there's no absolute max, which is weird because there's definitely an upper limit, but there's no actual value that's a maximum. So that's a weird thing that can happen to this function if it's an open interval, right? Here, I have a closed interval, but it's not continuous. So there is no absolute max or absolute min because of this vertical asymptote. Now, there might be a relative maximum, like here, like that's critical. There's definitely a relative maximum because there's a horizontal tangent line there, but it's not an absolute maximum. Okay, and notice here, this did have an absolute minimum, but it didn't have an absolute maximum. You have to be continuous and closed to get both an absolute max and an absolute min. Now, here, it's an open interval, right? So it's an open interval. That means I'm not guaranteed to have an absolute max or a min, but I do, right? I came up with it looks like a sine wave. So this one, even though it's open, I still get an absolute max, I still get an absolute min, but it has nothing to do with that theorem. They're critical, but there was no guarantee, okay? Here, again, it's closed, but it's not continuous. And this is another one of those like upper limits where there's definitely an upper bound to this function. I can't go any higher than whatever that value is, but there's no one value that's the absolute max because that's not part of the domain. So it's undefined at that instant, okay? I want to say there's 2 more. Oh yeah, So then this is like, you know, this, I don't know, reminds me like a slide at like a playground or whatever. But this has no absolute max or absolute min. It's bounded above, it's bounded below, but those aren't points of the function. Those aren't points on the domain, and therefore there's no absolute max or absolute min. And again, there doesn't have to be. There's no guarantee because this was an open interval. And then for the last one, similar idea. You're bounded by two vertical asymptotes, so it has to be open. Clearly, there's no absolute minimum. It does have an absolute max, right? But it's the way this function was designed. If you have a closed interval on a continuous function, you will be guaranteed to always have an absolute max or an absolute min. Sorry, you will be guaranteed to have both an absolute max and an absolute min. See, I call myself out, not just Andrew Lee, but also me. But if you remove one or both, then you can get weird functions. There's no guarantee. Okay, so homework then is just the next page. It's just practicing and again, analyzing those critical values where the derivative is 0 or the derivative does not exist.